Alright, the stream is starting. I'm surprised there's actually people watching right now. So, Taganzi here in the chat. Yeah, I did start or schedule a stream that started yesterday. That was a mistake. I meant to start it today, but just put it on the wrong date. So I deleted that after like 5 minutes. So anyways, the goal for this stream is to create a more physically based flight simulator than the one that was presented in that video. So if you're here, you probably watched my most recent video, which is about the flight simulator. And the way it works right now, this is the most up-to-date version, which I haven't made a video on yet. The way it works right now is fairly simple. All flight forces are basically just acting on the center of mass of the plane, which makes it very easy and controllable. And it's easy to implement, and it's fast to execute all this code. But it misses out a lot of complexities that come from real planes. So the goal is to create a physically based flight simulator. So instead of just having a lift generated for the whole plane or calculated for the whole plane, it's going to be calculated for each like segment of the wing. So like each wing, each elevator, each rudder is going to have its own lift generating. It's going to have an effect on the flight dynamics, but I don't actually know how that's going to hit it or how it's going to affect the flight model, but we'll just see how it works. So to start off with, I'm going to make a clone of the scene so we have something easier to work with that isn't a dogfight. All right, so this is the simple starting scene. And we do still have the old code here, so it's just a simple flight physics for right now. Okay, the first thing I want to do here is figure out where or how to design the code to actually represent the data that's going to be in the wings. So I'm thinking it's going to be a component that's just attached to game objects that are set around the plane. Yeah, so one of the examples of how this could be more advanced is that you could in fact stall one wing while maintaining lift on the other one, which will cause you to roll uncontrollably. If you yaw left or right, that will cause one wing to advance and have a different angle of attack, and it will cause that wing to generate a lot more lift. So these are things that are not possible in the current flight model, but they should be possible once we have the more advanced flight model. And additionally, stuff like the vertical and horizontal stabilizers are going to have their own effect on the plane's pitch, and it's just going to be much more like dynamic flying than this very like kind of rigid model that we have right now. So on this airfoil, the data that I want to add to it is so we're moving the lift power over here. Then you're going to replace this airfoil onto various game objects within the plane. So airfoil right here, and we're like, okay, so the plane right now has a lift power of 150 for the entire thing. If instead we're going to be placing these on individual wings, so this one, for example, could be over here and represent the right wing. So let's rename this airfoil right wing root. So wing root, because we can actually have multiple wings here. There are multiple airfoils here that represent different sections. So this could be the wing tip instead of the wing root. Then there's also going to be another airfoil section for the center of the plane, which is going to be the fuselage. Here's a fun fact about planes, or jet fighters in particular. The fuselage of the plane actually provides a substantial amount of lift, something like 20–30%. So some of this lift is going to be generated just by the fuselage alone, and not just by the wings. So I'm going to mirror this over to the other side as well. Okay, and then if we want these all to work, if we want these individual airfoils to generate lift, then we actually need to modify the plane script. So currently, the update lift function right here. This just calculates lift for the single center of mass of the plane. We need to update this, and as well as update the calculate lift function so that it works on multiple distinct airfoils. Also, in particular, I don't want to add like a fixed update loop to the airfoils themselves just for performance reasons. There's no reason to give these individual loops because they're pretty much only work in the context of the plane. So instead, we're going to be adding like a list here just for so the plane knows all of the airfoils that are inside of it. So the user just drags and drops the airfoil parts onto this list in the inspector. Will there be gizmos visualization? We could add that rather simply, but I wasn't actually planning on it. Like, there's not really much to visualize here other than the location of the airfoils. You can add a tagger, but I don't like doing that. Okay. So anyways, we need to actually put these airfoils onto the plane right now. Okay, so now that the plane knows about the airfoils, we need to actually use them somewhere inside the update lift function. So I'm just going to comment all of this lift code out first. Okay, so we need to expose the lift power that's inside of this function. So we need to, I don't know, make a property here. I'm just kind of improvising how this code is work. I haven't designed it that much, so this isn't really the best way to develop code, or the best way to like design how these data members will be exposed, but it will work for right now. Okay, so for calculate lift, we're going to be calling the calculate lift function, which already exists, but we need to modify this because we're no longer providing just these variables. So okay, so we can call the calculate lift function here. We get the output of it, which is the combination of lift and induced drag, and then we can apply this to the rigid body. However, unlike the previous method of doing this, we're not applying directly to the rigid body using add force. We're using add force at position. So what that means is that lift that's generated in this position, for example, will actually cause the physics system to apply a lift force right here. This is how a plane rolls. Whenever this wing generates more lift than this wing, it will cause the plane to roll. And that is applied by add force at position, which allows you to like, it's not just a force, it also calculates the torque that's produced by that force. So we need to apply the force, and then we need to figure out the position of this. We need to figure out the position of this game object so that we can apply the force in the correct location. So I think the easiest way to do it would be to expose the local position of the game object through here. Just from the airfoil's individual transform. We need to apply it as the offset from the rigid body position, while also respecting the rigid body's rotation. So we apply the rotation to the airfoil's local position. And hopefully this works right now. We should at least get airborne if we set up all the lift power variables here. So originally the total lift power of the plane was 150, and we have 5 airfoils here, so let's just divide by 5 and give each one 30 lift power. So once again, there's 5 different airfoils here. Each one is located in a slightly different spot. So when you're flying straight and level, all these forces will balance out and your plane will just continue flying level. But somehow, if a wing starts generating more lift, it will cause the plane to roll, and eventually we'll add extra airfoils for the stabilizers as well. But actually, I do want to do one more thing, which is I want to visualize the lift that's being generated right now. So we're going to use debug that draw line to just draw like a green line that represents the amount of lift force generated by each airfoil. So Oh, there you go. Those green lines show the amount of lift that's being generated by those airfoils. So that's very tall. I guess because the plane's very heavy, so you need a lot of lift to do it. Okay, unfortunately, we don't actually have pitch control yet, or rather, the pitch control doesn't work properly with these, with the way we're applying lift right now. So, the plane isn't actually controllable, and you can't take off yet. But we can at least see that the lift force is still functioning properly. At least it's generating some amount of lift. Hold on. So if we divide the lift force by the rigid body mass, it should make those lines a lot shorter and more sensible. Like we can actually understand how much is being shown here. Oh yeah, so we can see just the visualization is now a little more sane. Okay, so the next thing we need to do is hold on. Okay, one thing I want to do is hook up these airfoils so that each one is actually has a control surface on the back. So for example, on this wingtip here, the wing is the main part of the airfoil, but there's also the control surface, the aileron, which moves up or down to change the amount of lift generated. So once we have right now the only roll control is from the simple physics model we had earlier, but I want to get the roll control controlled by the ailerons instead. So the way to do that is to actually change that. Effectively, the way ailerons work in real life is that the aileron changes the angle of attack of the entire airfoil, which changes how much lift it generates. So we need a way to actually change the angle of attack that's going into this function in the calculate lift function. So angle of attack right now is just the direct angle of attack of the entire plane, but we need to change it for individual airfoils. So we're going to add another field here that just so we can like add a bias to the angle of attack that allows us to change the amount of lift generated by one airfoil individual from all the other airfoils. So we want to, and also each individual airfoil needs to have its own like input so that when the user rolls to the right, for example, it will cause this airfoil to move. And that input is going to be distinct from the input that this one receives. So this input will eventually be routed from the player's like roll axis. Okay, so instead of a float for the input value, we actually want a vector 3 because the player's input is represented as a vector 3 called control input. So in this case, the roll axis is going to be on the z of the input, but the pitch and the rudder axis, or the pitch and the yaw axis, are going to be on the other axis of this vector 3. So in this case, we need to add another field here to control how that control input is converted into a single float variable to control the AOA. So We're going to multiply this value, input influence, with the user control value, which will be in here. Let's rename it to input. So input multiplied by input influence. And then instead of taking like the magnitude or the direction of this, instead we're just going to sum each axis of this influence value to get the total amount of influence from each axis of the control input. This is kind of hard to explain. Hold on. Okay, so here's an example of how this is going to work. Input influence for the aileron control here is going to be, let's set this to -1 because it's on the left side. So just the z-axis is set to -1. So when the user says to roll right on their stick, that means the z-axis of the control input is going to be equal to 1. And we want this to be equal to, actually we want this to be equal to +1. So z times the z here, which is 1, times the z from the control input, which is also 1, equals 1, and then that gets summed with the influence x and influence y, which will be 0 because these variables are also 0. So it's just a way to choose which axis you want to influence this particular control surface. Oh, Gonza here, your comment about buoyancy being a list of points, yeah, that is kind of similar, just using different formulas, but you are basically summing the influence of buoyancy across the entire surface of the object, and for planes, you're summing the influence of lift across all the different airfoils, so very similar principles there, yeah. And I'm glad to hear that the PID video helped you, because I certainly helped myself when I had to research all that stuff to make the video. And all that PID stuff was like relevant to my day job, which sometimes is embedded software engineering. So, okay, so how are we going to use this input value to actually change the way this aileron generates lift? So we need to add another function here that calculates how much lift or how much AOA is being added, which will be added to the AOA value that the entire plane is facing. So the angle of attack here is just the AOA that's shared across the entire plane, but it can vary across individual airfoils if the user sets the input differently. So we're going to write that function right now that changes what the AOA is. So it's just like an AOA bias that changes how it affects the lift generated. And it's just a simple multiplication. So if the input is 1, because the user is putting 1 on the roll axis, then the full change of the AOA input range is going to be affected here. So we actually want to set this AOA input range to however far this flap moves whenever it gets deflected. Hold on. So the F-15 is this plane as a whole has, I set the input range, the AOA from so at 30 degrees we have maximum lift. So up to 30 degrees is what we can put for the AOA bias. So we go left wingtip here. I don't want to do full 30, but something like 20 might be a good value for this. I am just spitballing. I don't actually know what these values should be. Now, to actually have this run, we need to take the input value, which right now is recalculated in the update steering function. So we take the control input, we multiply it by all this stuff to just apply torques directly to the center of mass. But instead of this, we want to apply torque via all of the airfoils that are connected to the plane. So actually, I'm going to disable this function right now, update steering. And I am going to take some of the code from here. Actually, I don't need to take any of the code. I just need to read control input. Inside of this update function. So here, right before we update the airfoil, we need to actually set the input. So set input, control input. I want to see if this is actually sending the input correctly here. Hold on. No, it is not. Okay, so input is not being updated for some reason. Did I set this in the inspector correctly? Oh, it's because of this. Yeah, the plane's not moving, so we don't actually have velocity, so it's just rejecting on this return call right now. Okay, there we go. Okay, so we can actually see the input value changing on this, the wingtip, the aileron. Okay. So it's 0 whenever you hold neutral on the stick. It goes to one side or the other whenever you change your roll input. Okay, so now that we have this input that's going into the airfoil, you just need to use the AOA bias to change the AOA of this airfoil. So here, instead of angle of attack, we add airfoil dot AOA bias. And hopefully this will do something. Okay, it's doing something, but I don't know that was not correct. At the very least, you can see on this, when I move my stick to this side, it changes the amount of lift that's being generated by each one. But it's like really sporadic. I don't know why it's moving around yeah, I don't know why it's moving in that way. Oh, I know what it is. Okay. AOA bias, as I set it in the inspector, 20. That's 20 degrees of AOA deflection. But angle of attack is in radians, so I actually need to modify this. I need to change it from degrees to radians, which hopefully Unity provides that calculation right there. Okay, that's a little more controllable, but for some reason it's backwards from what I was expecting. So I guess I have to invert these variables. There we go. So the ailerons are actually controlling roll now. Although since we're still not able to fly because we don't have pitch control, doing that just crashes the plane. So then we need to add airfoils that represent the elevators now. And the input for these, instead of going on the z-axis, which is roll, it needs to go off of the x-axis, which is pitch. And the AOA input range, let's also put 20 here, because I don't know what the value should be. And this should actually change the amount of lift generated by the airfoils. And also you'll see that they are generating lift at all. No, they are not generating lift. Hold on. Oh, I need to add them to the list of airfoils. So this is error prone, but just as a first pass for what we're doing, this is fine. So we add them to the list here, and then we should be able to generate lift from the elevators. Okay, there you go. You can see the little green line growing out of the elevator. So those are also generating lift now. And it's also causing the airplane to pitch, but it's very hard to control that. Okay, I think I should make the ailerons a little bit weaker here. So just changing how much lift they change at the maximum input from 20 to 5, that should make it weaker. Okay, so I was just flying there, but it was incredibly unstable. And finally, I want to add the vertical stabilizers, which is just another pair of airfoils that we need to add here. Okay, but there is a complication here. Uh, so far, all of the lift surfaces that we've been adding are horizontal, but the vertical stabilizers are, of course, vertical. So we need a way to generate lift that goes sideways instead of vertically. And to do that, we need to actually like add some more stuff here, change how that's generated. So first of all, I'm going to add an enum to actually select the value. So we have horizontal, which should be the default, and vertical, which is going to be for vertical stabilizers. And then here we'll select which AOA to use based on this airfoil type field. So if airfoil dot type equals horizontal, we use the horizontal angle of attack. Plus the AOA bias from the airfoil. Else, if it's vertical, then we just do the same thing, but we use angle of attack yaw instead. And then we need to actually add these, the vertical stabilizers, to the list of airfoils. And we need to set this type value to vertical. So I don't want to give 20 degrees AOA range there. And they probably don't generate this much lift. But if we set this up correctly, where Y is the yaw axis, then we should actually have rudder control now. Oh, and by the way, you can't actually see the control surfaces being animated because I just disabled that part of the code, but the effects they have can still be seen with these green lines. Okay. Those vertical stabilizers are not generating lift correctly. No, because we need to change this vector right here. So right, vector 3.right is fine for the horizontal surfaces because it points to the right along this red arrow. But here, for the vertical stabilizers, we need to use vector 3.up since it points, they point upwards. And so we just switch this variable based on the airfoil type again. Okay, so the rudders are now working because I can yaw left and right. And the plane is very hard to control still because we're not really able to take off. And as each wing kind of swings around, it changes the velocity, it changes the amount of lift, and you just roll uncontrollably. So we still need a way to actually take off without crashing. Okay, so one more thing that I want to... The heck? All right, spammer in the chat. Okay. So one thing I want to add here is changing this flap. Right now we can control the aileron, which is used for rolling. We don't have a way to control the flap, which is used for generating more lift during takeoff and landing. And it actually functions the same way as an aileron, which is to say that when the flap goes down, it just generates more lift for this segment of the wing, but it's not controlled by the player's control input variable. It's actually controlled by this variable here, flaps deployed, which is just a separate control that only works at low speed. So for the wing root sections, we need to actually change how these control settings are, how the input is controlled to change where the flap location is. So this only works on control input. So I'm actually going to add another list up here, which is just for flap airfoils. And then instead of control input, we're going to be sending the flaps deployed variable, which is a Boolean. So instead of, we need to turn this Boolean into a float value. So flaps deployed, ternary operator, 1 or 0, and then the other parts of the axis, other parts of the vector 3 are just going to be 0. So whenever flaps deployed is true, it returns 1. When it's not true, it returns 0. And we set that on the x-axis. So we want this, the flaps, to work on the x-axis. And we want these to have a strong effect whenever they go down. So let's put this on 20 again. And now we have flap airfoils here, so we can add the wing root elements. And now those will be controlled by flap, and we need to remove the wing roots from up here in the regular airfoils. So what this means is that when the flaps are deployed, whenever, in this case, whenever you're on the runway and you have your gear down, the wing roots should generate considerably more lift, allowing you to actually take off. Okay, so you can see the wing root right there generates a lot more lift. Although for some reason we're crashing immediately. Okay, so I must have set something wrong here because only one wing is generated correctly. Okay. So now you can see that the wing roots are generating a lot more lift. Except it's still in the wrong direction. What the heck? Okay, now the wing roots are both generating a lot more lift because the flaps are deployed. Okay, so the way I think I can see what the problem here is. So even though we were taking off, we were gaining speed to take off, as soon as we try to even pitch up slightly, we lost a ton of speed because the induced drag, whenever your AOA is non-zero, you get a lot of induced drag, and that's just causing us to slow down and lose all of our speed before we can even take off. So let's just disable induced drag for right now. Okay, so what just happened there is that the plane pitched down whenever we gained a significant, even a slight amount of speed. That's because the wing roots are located pretty much on the center of mass of the plane. So there's offset to the side, but the z-axis, which is front and back, it was set to 0. So even though this was generating enough lift to lift the plane up, the elevators were also generating lift, which then pushed the plane downwards, and we lost control and crashed. So what we need to do is move the wing roots forward so that they are in front of the center of mass. And then the lift they generate should hopefully be enough to actually take off correctly without crashing. Anyway, this really wants to pitch down right now. And I just pitched up so violently that I tail striked, crashed the plane that way. So yeah, this is the main problem with physics-based simulations, is that if you aren't tuning it correctly, it's going to be very difficult to control. Okay, so this is a bug. That's not supposed to be going sideways. There must be some kind of issue with how we're generating lift right now. Or perhaps maybe the elevators are just too strong and sending us out of control. All right, so clearly there's some kind of bug in how we're flying this. The forces are in world space. That's yes, you're correct. So calculate lift is calculating the force in local space, but rigid body dot add force at position is in world space. So I do need to actually transform this correctly, which is just simply multiplying by the rigid body's rotation. All right, so thank you for that. And that should place the force in the correct direction even when the plane rotates now. There we go. We're getting a much more stable flight. Although when we take the flaps off, now we can see the elevators, or when they're acting as just horizontal stabilizers, are very strong. In fact, the elevators are very strong in general. That is not very controllable. Ooh. Okay. I think just in general, all of these lift surfaces are too strong. So we can probably just turn all of them down, reduce their strength. So instead of 30, let's do 20 here. And the wingtips usually generate less lift to begin with, so let's reduce that even further. It should make their rolls less strong and so more controllable. But we were actually flying there. It was just hard to control whenever you wanted to turn. And there's some crazy oscillations from the stability right now. So that horizontal stabilizers, they provide stability, which means that they want the bore sight and the velocity. It's trying to bring the nose of the plane to match where the velocity is pointing. Problem is that you're always kind of, that's going to cause you to pitch down, which is why we have a very strong pitching down movement. Okay, this is still very difficult to control. You can see that the roll force is still very strong right now. And the pitch force is actually pretty weak. So let's just, again, make the ailerons a lot weaker here. Okay, this is a little bit more controllable, but not by much. Okay, so one of the consequences of disabling the old steering system is that we no longer have the G limiter. So right now, I am pulling 11 Gs, which hopefully I can figure out a way to actually reduce the amount of Gs generated by these turns. And hopefully I can make the plane more controllable, because it's really hard to understand what I'm even doing here. Somehow it feels like the ailerons are still way too strong. And also feels like the elevators aren't strong enough. Okay, this is still kind of hard to control, especially in the pitch direction, but it seems like we're actually flying now. Oh, never mind. Seems like the elevators are still really weak here, but I'm not really sure. Like, I'm reaching the limits of my own knowledge of aerodynamics. So I don't really know how to make the elevators much stronger without making them too stable either. So we can see, like, even when I do that, I'm not actually giving stick input. When I hold it like this and then release it, the nose just oscillates up and down, which is way too strong of stability. Like, it wants to keep the plane aligned with its own velocity. And I need to figure out some way to break that so we can actually control it. Like, this is a problem that real planes have, where they need to be, or at least real fighter jets have. They need to be unstable so you can actually turn them quickly. Passenger airliners are generally want to be stable, but fighter jets need to be unstable. So I need to figure out a way to reduce stability. Okay, a very simple thing I can do here is just increase the angular drag that's on the plane. That doesn't really solve our problem, but it should make it, should like tamp it down a little bit. Okay, this is still very difficult to control. Calculate the stabilizer lift differently from the elevator. Not really sure what you mean by that. Okay, so on an F-15, the stabilizer and the elevator are actually the same part. There's just one part here, and really this thing just rotates to move the entire thing. So there's not actually a control surface here, although we're kind of pretending that it is. And here, like, we're kind of pretending that the entire elevator has a control surface, but on stuff like the vertical stabilizer, the control surface is actually a distinct part. So the vertical stabilizer is this fixed part, and the rudder is the moving part. For this is both an elevator and a stabilizer, which is, I'm not really sure what you mean as to calculate the lift separately. So this is, I mean, we're flying right now. We have pretty decent control of the plane. Just that it's very hard to control this whenever that stability is like oscillating back and forth like that, which is a, I know that's a problem the real planes have, but I don't know how they actually solve it. This is just barely controllable, especially when you get above 400 knots. It's like fighting me the entire time. If I pitch up, there's a huge AOA right now, but as soon as I release it, it immediately snaps back to 0 AOA. That's a very strong stabilizer. The plane is like positive stability, I think. It's just really hard to control, especially whenever it starts rolling uncontrollably like that. I was not telling it to roll right there, it just started on its own. So there's some kind of behavior error that I made that I can't figure out for right now. But we accomplished our basic goal of actually having physically based flight. It's just very unstable. Okay, something I can add here that might improve control a little bit is right now when you just move the stick, it just moves the input instantly based on the influence in the player input. So instead of that, I think I can add, well, there's a utility function I've written before, which is move to. So this just like slowly moves this value towards the target value. Hold on, let me actually write this out. So utilities dot move to and then we need a delta time and an input range. So we need to add this argument here, delta time. We need to add it here as well. Okay, so this will just like reduce the speed of how fast each control surface moves. So before it was moving instantaneously. Now with an input speed of 5, it will reach the full range of controls after 1/5 of a second. That probably isn't going to help the stability problem too much, but it should make it a little more controllable when it comes to rolling. Okay, it seems like it's not actually following my roll command very reliably. Like it's just ignoring rolling sometimes. Um, okay, one thing I want to do is actually set the animation because that was disabled when I disabled the old steering system. So the animation system just reads this value effective input. It's not really all that important, but it means I can see the flaps and the ailerons moving around whenever I'm flying. Oh, you know what it is? I can't really change the roll whenever I'm pitching because the wings are loaded. I need to actually unload the wings before I can change the roll direction. Okay, so that's a property I wasn't actually expecting to handle, but it does work correctly now. So I need to actually release the pitch input before I can start rolling, which is something that you have to worry about on real planes as well. And if you don't do that, it will just kind of stick to the same roll input you gave it earlier. So yeah, you do need to unload your wings. Although just in general, this plane is still kind of hard to control even when you do that. I'm just testing out the rudder right here. It doesn't seem to be very strong. Like it's not actually turning the plane very quickly, which is fine. That's kind of how rudders. I mean, rudders don't actually. They aren't really supposed to be used at 700 knots, not at full rudder input. Try having different lift coefficients. That might work because right now we're sort of using well, actually, what do you mean by lift coefficient? Do you mean the lift power here, or do you mean the lift coefficient that's actually calculated inside of here? Because that depends on the AOA. And for simplicity's sake, so far, I've just had one AOA curve that's shared between all the airfoils. I don't want to have to define a new AOA curve every single time. That might actually work to like fine tune the behavior of each airfoil, but it also sounds really tedious. Okay, something I want to simulate as well is that when oh, hold on, lift power depending on AOA. I'm still not sure what you mean because lift power is like the user defined variable that just allows you to fine tune it. Um, the AOA curve is also user defined, but that is used to both of those are used to calculate lift coefficient. Okay, so one other thing that I want to calculate here is the effect of wing sweep on the lift that's generated. Right now, I do kind of simulate this right now with project on plane, but it doesn't really. Again, this is just it just takes the global local velocity and the direction you're facing, and it just calculates the effect of like if your entire wing was completely flat and had no sweep angle, that's what this function is currently doing right now. Instead, we want to have a separate sweep angle for the left wing and for the right wing. And so that whenever you yaw, one of your wings will be more flat on into the wind and it will generate more lift. And that's like a special dynamic effect that's it can only happen whenever you actually do a full, like a physically based simulation instead of the old way I was doing. So to do that, basically what that means is the angle of attack yaw of the plane needs to be combined with the wing sweep, and that needs to be used to modify the lift velocity here. Okay, so I did some research beforehand, and the way this is supposed to work is the local velocity, like the effective airspeed, is modified basically by a cosine multiplier of the angle of attack, or rather a cosine of the wing sweep. So mathf.cosine, and then we have to put it something here for the wing sweep. And note that your angle of attack yaw also affects how the wing sweep goes. So whenever you yaw, for example, if you yaw like 20 degrees to the left here, that means your right wing is now flat on into the wind and generates more lift, and your left wing generates less lift, and that causes your plane to roll to the left. So to do that, we actually need to pass angle of attack yaw into this function. So for AOA here, we already have the switch here. So for horizontal airfoils, the angle of attack it uses the regular angle of attack, and for the vertical stabilizers, it uses angle of attack yaw. We need to have a switch here so that the angle of attack gets chosen correctly depending on vertical or horizontal airfoils. So first off, let's call this angle of attack sweep instead. We have AOA sweep equals angle of attack yaw. And likewise, on this part of the switch, the AOA is based on the attack yaw, but the AOA sweep is based on regular angle of attack. And then we need to actually add a property to the airfoil, which is the sweep angle of the wing. So for example, the right wing is going to be swept at 45 degrees, and the left wing is going to be swept at negative 45 degrees. Oh, Y485 is in the chat. Yeah, thank you. Yeah, thank you, because I played Tiny Combat Arena a bunch, and also the other earlier Tiny Combats, and that's actually what inspired me to start writing my own flight simulator. The compile error here because I didn't actually fill out this variable. So hold on, just angle of attack yaw for right now. I'm going to put AOA sweep here as well. And then on the wing root and the wing tip, on the right wing, we want to put 45 degrees here. So for the left wing and the left wing tip, I'm going to put negative 45 degrees. And likewise for the elevators. So hopefully, whenever we yaw to the side, we'll actually see some kind of effect on here. And never mind, I just crashed. Just crashed while taking off. That's embarrassing. Okay, I'm not really seeing the effect I want, but also the yaw is way too weak right now, so I can't even get the nose pointed too far to the side. Oh, and you know what? I forgot to actually change AOA sweep. I need to actually get the sweep angle from the wing, so I need to expose this. Okay, so we take the sweep angle property, and we simply add it onto the AOA sweep. Now we need to convert this from degrees into radians as well. And we need to do that for both sides of the switch. There we go. Okay, so that fixes the code part, but I also need to make the rudders stronger. I could put a sweep angle on the rudders as well, but that doesn't really have too much of an effect because they're swept vertically, so I don't really care about that. Okay, let's increase the AOA input from the rudders. And hopefully we can actually see the effect I want. Okay, I need to stop crashing on takeoff. Plane is still very hard to control on the pitch axis, but I'm just going to ignore that for right now. Okay, the rudder is still incredibly weak. Oh, there we go. Okay, so when I put rudder input in, it actually does cause the plane to roll just a little bit. The effect's really weak right now because the rudder is still kind of weak, but we are seeing the effects of wing sweep on the amount of lift generated. Yeah, so if I roll to the side, if I roll to the, or if I yaw to the right, it's causing me to, it's causing the right wing to roll upwards. That's not correct. No, hold on a minute. I think I know the problem here. Okay, so since the rudders are located above the center mass of the plane, rolling just kind of pushes it like torques the plane to the side. So when I give rudder right, it causes the top of the plane to roll to the left because the rudders are located above the center of the mass. It's acting as a giant lever. However, it doesn't seem to be actually changing the amount of lift generated by the wings just because the rudder isn't pushing the nose to the side far enough for the wing sweep to change. But yeah, this is a very complex system where there's like the rudder wants to roll in one direction, but the wings want to roll in another direction. And it just becomes very, there's so many different forces acting on the plane at the same time. It's also kind of hard to balance how much each one is doing because we're like calculating from first principles amount of lift on each airfoil instead of just how much like rudder strength we want, which is how the old system worked. But we are seeing some dynamic effects so far right now. Yeah, so Y485. Yeah, this is a very complicated rabbit hole I'm going down right now. This is just not an easy way to fly the plane. It's much harder to control. And so far what I found right now is that the pitch axis in particular is really hard to control because basically as a stabilizer, it's way too strong. So it basically points the nose directly towards the velocity at all times, and there's just a slow pitch down movement, even when I'm not touching the controls. That is realistic because I haven't actually implemented stuff like elevator trim yet, but it's just in general that the pitch stabilization is really strong. So for example, if I just pitch up, I get like 14 AOA, and when I release it, I immediately snap back to 0 AOA. And like I've never flown an F-15, but it seems like that's a little bit too strong, and like it wants to stay in the same orientation a little bit too much. And I'm gonna be honest, I don't actually know how to break or how to limit or what's the word, decrease the stability of the plane any more than what I've already written right now. At the very least, though, I could do something simple like adding elevator trim to stop the nose from just pointing downwards, slowly pitching down at all times. So that would actually be pretty easy to implement right now. By just adding a trim setting. Unfortunately, I don't have a way to control the trim from like the player input in real time, so we just have a fixed trim setting for the entire flight. So here for AOA bias, where it's based off of the input and the AOA range, but also the trim. Yeah, it'll work as intended, and you'll discover why planes are laid out how they are, and subtle things like why trim is required, or why wings are actually subtly angled for cruise. Yeah, I am in the process of learning that right now. Like I've read basically why stabilizer is located at the rear of the plane, and why like canards at the front of the plane make the plane less stable. But actually, like fine tuning the parameters is rather difficult because of course I don't know how an actual F-15 flies, and I don't know how much lift these surfaces are supposed to generate. So I am just spitballing on every number right now. But once we have the trim setting on the elevators, set this to, I don't know, 5. I don't know what this actually does. Ooh, that is a very strong trim down setting. Hold on. Let's try -5. Okay, there we go. So now the bore sight, this little W-shaped symbol right here, is about 5 degrees over the velocity vector, and that's caused by trim. And that is something that real planes have to deal with, is setting the trim as you go through different phases of flight. When I play simulators, I find that to be really tedious, and I just don't actually want to do that in a game. But it appears that with this physics-based code, you do now have to actually worry about trim settings. And we're actually seeing some dynamics here. The trim is actually pitching me upwards because I'm not giving input right now, but the trim is causing me to pitch slightly upwards because I was going at different airspeed, so you need to change trim as you go through different airspeeds. That's the general gist of it. It's just impossible to do that right now because I don't have a way to do it except by changing the inspector. Hold on, if I slow down right now, I should eventually reach a point where this trim is perfect for the altitude, or perfect for the airspeed. So like right now, we're not pitching up or down right now. So trim is basically perfectly set at -5 degrees for 300 knots. If I go faster, the trim is going to want to push me upwards. If I go slower, the trim is going to pull me downwards. And I really don't want to add a way to actually set the trim in real time. That's just going to be, I'm going to leave that at like a fixed value that kind of works at some airspeeds. So let's just leave that at like -5-ish. I'm not sure how this works in a plane like the F-15 since it's not fly-by-wire. With an F-16 fly-by-wire system, I guess, it has a cool effect of automatically trimming the plane by its nature. Yeah, that would be cool if I had some way to automatically trim. Um, but I have no idea how you would write something like that. Yeah, a lookup table probably would be the simplest way to do it, but that means I would need to actually just fly different airspeeds and record the trim setting each time, and that sounds like a lot of work, especially because I'm just kind of doing this off the cuff right now. But okay, so we have trim figured out. I still want to figure out why yawing is not causing the plane to roll in the correct direction. So, okay, just as a little cheat right now, I'm going to change the rudder, the vertical stabilizer, so they are not above the center of mass. So they're in line with the center of mass right now, and you shouldn't have any rolling torque just from using the rudders. I want to see it only happening from the wings. So as a reminder, whenever you yaw side to side, it's going to, oh my god, what is happening? Okay, so I just lost control even though I wasn't giving any input at all. Okay, something weird is happening there. Okay, I must have done something wrong here. I must have set one of these values incorrectly because now we're rolling, even though it's should not have this effect. Was it really just because I moved the rudders downwards? Okay. So now we're have the more physics, more problems. That's the problem with these physics-based systems, that tuning them or debugging them is going to be a real pain in the ass because I don't know what's actually causing the plane to roll right now. Oh, I set the trim on the rudders to different variables, so, or I set the trim on the elevators to different values. That's what was causing it to roll. Yeah, on F-15 in particular, the elevators can also be used to roll the plane, not just the ailerons. So you'll see on like real footage, the elevators will turn in opposite directions to help roll the plane. And what I was doing right now was kind of I was accidentally rolling the plane because I had different trim settings on them. Okay, so back to the rudder problem. I want to set these so they're the same as the center of mass, and then see if we can get the sweep angle to change the amount of lift generated. It does not look like it's actually rolling side to side very much. So there might be a bug in how I implemented the sweep angle here, or there might be something else entirely. Okay, let's rename this to sweep angle, because it's calculated from the sum of angle of attack yaw and sweep. Oh, that's the problem. I am not actually applying the sweep angle to both sides of this switch. Okay, so now rolling is producing a slight, or rudder input is producing a slight roll input, but in the complete opposite way from what I was expecting. So wait, if I rudder right, that should make the left wing produce even more lift, but it's doing the opposite. The right wing is getting more lift. Are you using the physics engine or just calculating and iterating forces yourself? Both, kind of. The velocity of the plane and the torque, or the angular velocity, is controlled by the Unity 3D's rigid body system. But other than that, all of the forces from the airfoils and such, those are being calculated by my code. Okay, so somehow the sweep angle is like the opposite of what I was expecting it to be. Okay, hold on. One thing I can do to check this is actually just step through the code in a debugger. I need to not crash on takeoff if I want to do that. And stepping through this code is kind of painful because I have like, I don't know, 10 different airfoils right now that are all acting on the plane. I need to figure out which one is not generating the values correctly. It seems like the wings, I mean, I know the wings aren't generating the value correctly, but I need to figure out where the bad values are coming from. Okay, so this is the airfoil on the fuselage. That's not relevant. Airfoil on the right wingtip. Okay. Okay, so angle of attack yaw is this small negative value, while sweep angle is going to be a positive value. Large, I mean, this is 45 degrees and this is minus 0.02 radians. But for some reason, the signs are different, so not really sure where that difference is coming from. Okay, we can see that the velocity vector is to the left of the bore sight, so that means the right angle, or the right wing, should be more direct on into the wind, which is correct. Whenever the left, but for some reason it's doing the opposite of what I'm expecting here. See, I should be rolling to the left when I give left rudder, but it's rolling me to the right. Because the left wing is generating more lift, though it should be more, like that should be facing left, or it should be less flat on into the wind, so it should have like a smaller lift generated. So, well, a very simple thing I can do right now is just take these wing roots, take all these airfoils, and change the sweep angle. So instead of 45, it's now negative 45 and vice versa. And maybe that will solve the problem and just never think about it again. I feel like Unity should have a debug text for these kind of use cases. I mean, yeah, but in general, programming is very hard to, whenever you're trying to, if you want to visualize a bunch of different individual forces like this, stepping through a debugger is always like really inefficient. So that's what these green lines on the wings are. These are the different sections of the wing and how much lift each one is generating. And for like game programming, this is probably the simplest way to visualize forces like this, is to just like draw something in 3D space. But yeah, there are certainly cases where stepping through a debugger will make it easier. Okay, so just by changing the sweep angle of the wings, or by inverting them all, now I get the expected behavior, which is right rudder causes a right roll. And we can go back and change the vertical stabilizer to be above the center of mass again. And see if this actually has the correct effect, even whenever they're producing torque in the opposite direction from their vertical offset. Ooh, now that's strange. When I give rudder input initially, it rolls to one side and then it starts rolling in the other direction. So if I give right rudder, it rolls to the left for a split second, then rolls right. I have no idea what kind of dynamic, like aerodynamic force would cause that. But apparently the physics system that I've written so far thinks that's the correct way to handle it. To like, somehow this is coming out of all the forces that I've added together here. But this is basically what I was looking for. So when I give right rudder, it also causes the plane to roll to the right. And as a side effect, I haven't talked about this yet, but when I get roll any amount, we get a slight banking effect. So the plane will start turning to the right slightly, just from rolling to the right. And again, that's an effect that appears on real planes, and it's just very finicky here. But it does happen. So if we hold a slight roll angle, you can see that at the compass at the top, I am slowly moving towards the right, but also the plane is slowly rolling level. Again, that's another like stability thing. It just wants to turn level, even if you're not giving input. And that's another property that you can find on real planes, and that has been, I guess, successfully simulated here. I'm not really sure if a real F-15 has this property of wanting to roll level, but it is kind of cool to see the like emergent behavior of all these aerodynamic properties here. Okay, so that's basically what I wanted to implement for today, but there is one thing I want to do right now. So I haven't made a video about this yet. Like, so far I've only released part 1 that shows the simple flight simulator. But I do, like, on my blog, on my personal website, where I've already written about part 2 and part 3, which is basically the end result is that you, oh my god. The end result is that you'll actually be able to dogfight with an enemy AI. So this is basically part 3 of my blog, is that implementing this AI, and it will shoot at you, and it's pretty good at shooting you down. Like, I haven't put any real limiters on the AI, so it's basically perfectly flying at all times. But now with a physics-based system, I don't know how smart this AI is going to be. Like, it might not even have, it might not know how to handle a physics-based system correctly, because I only wrote it for the simple flight sim. Seems like he's flying competently enough. I'm going to turn this visualization off so I can get a better look. Ooh, I still have induced drag set to 0, so I'm going to overspeed quite significantly here. I can imagine making the AI be able to dogfight after physics is going to be really tricky. Probably yes. I mean, the AI I wrote is really simple, but it's not going to know how to handle small, like, all those little oscillations and those aerodynamic effects I was talking about earlier. So uh, I may not ever rewrite this AI to handle physics effects because I just don't know how to write an AI that can handle that. Okay, one thing I want to do is re-enabling induced drag because I have it set to 0 right now, and that's not correct. It allows you to maintain speed even when turning. So don't really know how induced drag is going to affect this right now. I can just check. Oh my god, that's so strong. I just lost all my airspeed from a slight turn. Okay. And the AI is also crashing because he doesn't know how to, because his slight turn also caused him to lose all of his airspeed. So I need to figure out the right way to handle induced drag here. Oh, you know what? Because induced drag right now is like a variable on the plane itself, which is right here. Induced drag is 75. But since I'm applying this on every airfoil, that means I'm getting a large amount of induced drag on like 10 different airfoils, which is not good. So instead, I need to define induced drag just for this one airfoil, or so I can define it individually for each airfoil. Induced drag curve just reduces the strength of induced drag at low speeds. I don't really need to remove that right now, so I'll just add a new variable here. Induced drag. Let's rename that induced drag power. So instead of using the one single value for the whole plane, we can define induced drag on each individual airfoil. And I need to actually send it whenever we call this function right here. So airfoil dot induced drag. Okay, now we can fill in the induced drag variables for each of these, which originally I had it at 75 for the one, for just the whole plane. Across these, I probably need to divide it. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, so I have 9 airfoils. So, I mean, we don't need to we don't need to have exactly 75 divided by 9, but let's just put like 10 for here. Oh, whoops. Okay, so the wing roots also have 10. Let's say the wing tips have 5. These values I have, they don't really correspond to any like physical measurement. They are just like numbers for me to hand tune them, but I have no idea what a proper value for any of these would be. So let's just, again, we're going to be spitballing all these values. And that's still really strong. I could reduce it on some of these airfoils. But I basically went from 400 knots to 200 knots like in a second. That's way too strong. Okay, yeah, I seriously need to reduce the strength of all these. I've been working on a flight sim too. How are you handling stalls when there is no lift curve? Not sure what you mean by that because at least on the code that I've written so far, there is a lift curve, which is the lift AOA curve. So at zero lift, or at zero AOA, you have zero lift. At 30 AOA, you have maximum lift. And I don't know if you watched the flight sim video that I've already put on my channel, but it goes over like the basic theory of how the lift curve affects flight. Uh, so yes, whenever you go beyond the 30 degrees AOA, you will hit the stall region, and that's what causes stalling. But I need to reduce induced drag on all these parts again. Actually, let's just set it to 0 for a bunch of these, because it's still really strong. See, I want to tune induced drag right now and then get into like a dogfight with this AI that I already have and see just how it can handle regular, how it can handle this physics-based flight simulation. I'm going to guess it can't because I can barely handle it, and I just wrote it, and I wrote the AI, and I know that it really doesn't do anything smart when it comes to inputting controls. But this guy is firing a missile at me, so I think I have induced drag set to a good position here, so I'll continue this fight. The other problem with the AI that I've written so far is that since we have identical planes, we just have identical flight characteristics, so it's very easy to just get into a position where you're going in infinite loops because neither one has an advantage over the other. Except since the AI just like flies the perfect arc towards the player at all times, it's very easy to like the AI doesn't make a mistake, but if you do, eventually the AI gets an advantage. So here the AI just fired another missile at me because he already has an advantage over me. And I don't know if I can actually reverse this fight because I can barely fly it as it is right now. Oh, the rolling is really weak right now. Even at high speeds, the roll should be a little bit, it should be stronger than that, but I can barely roll the plane at all. What are you using to draw your UI? This is just like basic Unity UI. So I just made these like green shapes, like in GIMP. It's just basically just pixel art, and then I just position it using code which I haven't made a video on it on YouTube yet, but it is covered on part 2 of my blog, which explains what all these different UI elements do and what you're supposed to like what information it's conveying to the pilot. Because it is based off of both real fighter pilot HUDs and also like games like Ace Combat where you can see HUDs just like this. But in terms of what am I using to draw it, it's just Unity. So I cannot get any kind of position on this guy. And I don't think I'm gonna beat him, but I don't think he can beat me either. I think the best chance I have is trying to like force him to fly towards the ground, and maybe uh, he'll either crash or he'll just like go into his ground avoidance function and just steer in a way to avoid the ground, but it makes him an easy target. That's basically the only chance I have against this AI. I mean, in general, the AI I've written isn't very good, and that's the only way to do it even before the physics sim. But now with the physics sim, it's just like, it's way harder to fly this. Can you shoot? Yes, I can shoot. You have guns and missiles, but I'm not in a position to actually shoot at him yet. He's been shooting at me, but I haven't been able to shoot at him. Okay, so one thing, yeah, like I said, this AI has a function where if it detects it's about to hit the ground, it just goes into like a special ground avoidance function. And if I can take advantage of that, then I can maybe win this dogfight. Actually, it looks like he just crashed into the mountain. So the ground avoidance function that I wrote before is not able to handle the new physics-based flight sim because he was trying to avoid the mountain and then he crashed into it. So that's a terrain kill, but it's only because the AI I wrote is really bad. Maybe enabling Unity's dark mode would help. No, I don't live in a cave, so I don't need dark mode. People who need dark mode are weak. Okay, so I just shot that guy down in a head-on pass. That's basically the only opportunity I've had to shoot at him at all. No, I'm gonna crash. Yeah, so this is a much more complicated flight model than what I had before, but it's also way harder to control just because I don't really know how to tune it. Okay, so that's one missile. It missed. Yeah, no damage off of that. I'm gonna see if I can try to shoot him down with guns. Oh, this is so hard to control. How did you make the arrow? You mean the green arrow that's like pointing at the target off screen? Um, that basically just takes the position of the enemy target in the player's camera, and if it's slightly above the camera, it still has a position, and it knows that it's uh, like it knows how far off screen the enemy is, so it just draws an arrow pointing towards that point. I do have this written on my blog at part 2 for the Flight Sim series, but I don't have a YouTube video about it yet. I will be making one of those shortly. Yeah, I cannot get a angle on this guy because we both have the same exact turning performance. So we're just spinning in circles here. Okay, I need to make the roll stronger because I can barely control it as it is right now. All right, I'm going to try to shoot this guy down either with guns or with missiles, and after that I'm going to end the stream. I need to actually get into a position to shoot him first. Okay, that was a hit on the missile. The way the health system works, you need either 2 missiles or like 10 bullets to kill him. So I just took off 50% of his health. This is actually way harder to fly now that I've increased the roll strength. Yeah, that's real difficult. So using this physics-based sim makes it way more difficult to fly the plane, way more difficult for the designer to set the values up as they want, but it is an interesting exercise in all these aerodynamic properties. See, I just crashed because I'm struggling to control the code that I just wrote. Ugh, this is really sensitive. And there's a lot of oscillations between what I'm doing and it's just really hard to control right now. Maybe, I don't know, in a future stream I could try to figure out why this is so difficult to control, but I think we have a good place, a good amount for right now. So I'm going to try to shoot him down. I just want to be able to shoot him. I'm absolutely struggling though. He's actually shooting at me because I just keep on making small mistakes. And I just cannot get a good angle on him. Yeah, as I'm turning right here, you can see he's basically staying the exact same spot on my camera because we have the exact same turning performance because he's also flying an F-15. It's just the same plane for both me and the AI, so I don't think I'm going to be able to get him. I'm not sure if I can actually shoot him down because I can not control this code as it is. I'm going to give it like, I don't know, 1 or 2 more attempts. Somehow I have better control with the rudders than I do with the actual ailerons. That's probably a sign that I've designed the system, or that I've set up the actual lift parameters badly. Oh, he crashed. All right, that counts as a terrain kill, so I'm going to call that a night. Thank you everyone who came to the stream. Thank you Y485 because I've been I've been playing Tiny Combat Arena for a while. And thank you for all the people who gave advice during the stream. And you can look forward to seeing the part 2 where I'll explain the UI and part 3 where I'll explain the actual AI system. I'll be making YouTube videos for those eventually. And what I've done tonight, making a physics-based sim, that's potentially, if I can figure it out, that's a good topic for a part 4, which I haven't even written about yet. But if you've found this interesting so far, you might find it interesting later. So thank you for coming to the stream today, and I'm going to end it.